Welcome back to Advent of Code 2024, day 18. We're in the final days, the final week. And I am trying to break the record for the most number of different hotels streamed from. As you can see, I am yet again in another one. Hello, Quest Opus. Almost there, yeah. But we've got a tough week to go, I imagine. Yesterday's problem was pretty tough. Although, now that I've looked at some solutions, I realize it was simple to code, hard to reason out. So, 18. It hurt my brain, yeah. I mean, today, when I had a fresh, when I just, cleared everything off the stack in my brain and had a fresh look at it, it suddenly seemed a lot simpler, especially when some of the YouTube comments were explaining things to me. And I also realized that whole thing with the binary strings, I didn't really need to do that. That was just me visualizing the groups of digits. You can keep everything in decimal, just do repeated multiplications by 8. But yeah, the general rule of thumb is whenever you have a problem and you kind of hit a wall, usually the answer is it's going to be some variation of dynamic programming or recursive backtracking, because they're always conceptually the most difficult things to map out in your head, but reasonably okay to program for once you actually understand the iterative step or the recursive step. I was convinced for some reason that each answer depended on only 6 bits and lost a lot of time working that. Oh, right, yeah. Yeah, I guess that's one bit that's still tricky. The fact that it relies on the entire number up to a point, so you do have to... you can't split it up as independent problems, no. You're completely independent problems. But the branching factor is quite low, because I did it by hand. I branched by hand, and I was going back whenever I couldn't find digits and increasing the amount, and I did it by hand, so clearly the branching factor is only a few. Right, 18. RAM run. Oh goody, it's another grid problem. Good thing we've got a whole... I've developed a grid class and a vector class over the course of the last couple of weeks. You and the historians look a lot more pixelated than you remember. You're inside a computer at the North Pole. Is this going to be a Tron thing? Are we going to be on Tron bikes? 2017, day 2. Just as you're about to check out your surroundings, a program runs up to you. Oh man, these mugs that they gave me in the hotel, you can't... It doesn't have a handle, and it's too hot to hold. I have to wait for my coffee to cool down. This region of memory isn't safe. The user misunderstood what a push-down automaton is. Do I remember what a push-down automaton is? I guess I must have studied this at some point. I don't remember the term. This is like programming languages 101, where you learn like formal theories and parse trees and stuff like that. Okay, well, we don't need to know what it is right now. And the algorithm is pushing whole bytes down on top of us. Run! The algorithm is fast. It's going to cause a byte to fall into your memory space once every nanosecond. We've got a YouTube link. Alright, I might watch that offline. Fortunately, you're faster, and by quickly scanning the algorithm, you create a list of which bytes will fall in the order they'll land in your memory space. Okay, nice easy input. Your memory space is a two-dimensional grid with coordinates that range from 0 to 70, both horizontally and vertically. However, for the sake of example, suppose you're on a smaller grid. Each byte position is given as XY coordinate, where X is the distance from the left edge and Y is the distance from the top edge. Okay. You and the historians are currently in the top left corner of the memory space and need to reach the exit in the bottom right corner. So we're at 0, 0, we want to get to 70, 70. So the input... The only annoying thing is the width is not stored in the input, so I'll have to manually change that. Or you could take the max... Well, wouldn't necessarily have. Okay, so... As bytes fall into your memory space, they make that coordinate corrupted. Corrupted memory coordinates cannot be entered by you or the historians, so you'll need to plan your route carefully. Oh, okay. I've done something similar to this before. For coding game, actually. It was like a Bomberman. It was the Bomberman game. Where you're trying to find paths which don't cross over exploding squares at a time in the future. In the above example, if you were to draw the memory space of the first 12 bytes, it would look like this. Okay. You can take steps up, down, left, or right. After just 12 bytes have corrupted locations in your memory space, the shortest path from the top left corner to the exit would take 22 steps. Here is one such path. Okay. Simulate the first kilobyte falling onto your memory space. Afterward, what is the minimum number of steps to reach the exit? Interesting. So it's really just as such, but your neighbor function has to take into account how far you are, how long it took you to get here, and use that to know the history of when a space will be corrupted. So it's just a tweak of standard BFS, really. You could even make it into A-star algorithm, but I don't think we need to do that. Using the Manhattan distance. That would probably make it faster. Okay. Okay. So we want to copy our grid. Do we even need a grid here, really? Like, it's a grid without obstacles. All that matter are the... Oh, well, it does have width and height. Okay, we'll just use the pos class. Pos has like inbounds baked into it, so I've got this. We probably don't need most of these. We're not going to be using a priority queue, we can probably get rid of that. Get neighbors. So get neighbors will want to check for inbounds. Hello, Metal M. Oh, we don't need rotation. I think I just need to tweak this. How did we do it before? Here we go. There we go. So, are we using X's and Y's? Let me just take this method down. I'll stick to whatever variable type they're using in the problem. Okay. Okay, so NM is defined as a constant. It's going to be 70, 70. So we know this stuff. Relaxing day to day. Yeah, part one looks straightforward. It's just going to be another EFS, I guess. Copy stuff from before. Well, what I did before was DFS, but I mean, I've just changed the stack to a queue and then it's BFS. Okay, so we'll just... So these are... Eric felt bad for the last day. Maybe. I guess it's hard for Eric to judge how hard his int code problems are. But I guess that's why he has playtesters test them out. Okay, so when exactly does the first one fall? Well, at time 0? I assume at after time 1, once every nanosecond. Let me look at the example. Yeah, that makes sense. So at time 0, nothing has fallen. So I guess what I should do... Commenter last night suggested just buying cloud time for brute force. Eric said that someone must have been a tester did that, just that, and spent $81. I think I saw some post somewhere on Reddit. Someone used a big GPU to brute force yesterday's problem. Yeah. What was the number? It was like 8 to the power of 16, so that's 2 to the 3 times 16, that's 2 to the 48. So that's 2 to the 10 is 1,000, so we're talking about like, don't know the Latin name, Latin terms, but yeah, big number. 48 bits, yeah. Alright, yeah, I'll get rid of this. Alright, so. Well, let's just copy the. So we want. So how do I want to store these? I guess we want at a certain time. They said only use the first 1024. So like the first 1024 bytes, that's fine. Okay, so we'll write them all. Okay, I think the best way to store these is just a map from a pause to a time. Yeah, because then we can look up a pause directly in the map. So we want bytes. What's that? Then we want for I line in enumerates FW lines. It's going to be X, Y. So, and then we want bytes of pause xy equals I plus 1. So that's the time at which that becomes corrupted. And then so we basically want to define BFS from a starting point to a goal. And we can say we have obstacles like that. So, alright, so BFS probably going to use a well, what's the one people were suggesting to me? Heap DQ. Where's that? From, is it in heap Q? collections, yeah. Okay, so Q equals Q dot put start Q dot what? Append. Oh, you still use append. Okay, fine. So it's same methods as a list, essentially. All right. Q dot append start. We want a dist table, don't we? Right. While Q. Are you allowed to do that? Just say while Q. Current equals Q dot pop left. If we can do the goal check when we add it to the queue, just saves a bit of time. All right, so for neighbor in current dot. So we want get neighbors. So these are going to be inbounds. First, we want to check whether it's going to be corrupted. So if we move to a space at time 1 and the space becomes corrupted at time 1, I assume that's now invalid. That would make sense. So, so we're saying if obstacles oh no, this is not a default dict, and we shouldn't use the default dict either, unless the default value is going to be like infinite or something. If neighbor in obstacles and obstacles the time at which neighbor becomes dangerous is less than or equal to dist current plus 1, then we skip this one. Okay, so then it's a valid neighbor we can go to. Let's check that we haven't been before. If neighbor in dist continue. All right, dist neighbor equals dist current is 1 q dot append neighbor. Oh, goal check. If neighbor equals goal, return dist neighbor. Is that all we want? The distance, yeah. So we would never need to wait, like stand still. Like things are falling in order, so there's no reason to ever wait. If there exists a route, then the shortest route is one in which we never wait. We just keep moving and we don't loop back on ourselves or anything like that. It would be a different story if things started disappearing. Okay, so that's it. So on principal BFS from start, from 0, 0, 0. So we want only the bytes for the first 1024. So we want to say KV4. K4. How do I phrase this? KV in bytes dot items if v is less than or equal to 1024. Does that even make sense? Yeah. Okay, just say cap equals 1024. Parallelize 17.2 and brute force solution estimate drop just to 7 days on a single CPU. 138? Does that sound about right? Yeah, it's the right kind of magnitude. And it's 140 would be like a straight 70 by 70, so it's mostly a zigzag path without much looping back, with almost zero looping back. Sounds about right, although I was expecting a bit more looping. It really depends how often they drop. I suppose they have to really drop a lot before you actually create corridors and stuff. Yeah, so actually that does sound about right. Huh? Answer is too low. It is a bit low. Wait, it's impossible. Yeah, it can't be lower than 140, can it? Huh. Well, absolute minimum would be to go straight. Okay, so got something. Well, no, that's perfect. That's too perfect. But that's how long it would take. Yeah. It would be 69. Yeah, so that's how long it would take if there were no obstacles. So I've done something. Basically, my obstacle check has probably failed. If neighbor in obstacles. different obstacles. So is this happening? Let's see. Print current neighbor. Have we ever seen this? We are seeing it. Okay, that's a good sign. Alright. What's the time we're getting as well? So these are the times at which they are appearing. 46. What? Oh, yeah, okay. 53, 59, 53, okay, fine. Right, so the obstacle map seems to be correct. It is very suspicious, though, that we are so quickly getting to the end. We are hitting obstacles, though, but it seems we're kind of weaving around them without going back on ourselves. Guess we try the test example then, but there's not much code here, so I feel like if there should be an error staring at us in the face. While Q. Something's wrong about this neighbor check, though. There must be something. Continue. Let me just read the description again. Hang on. Oh, I don't think we're supposed to... So they say a byte falls every nanosecond. But do we actually start moving at time 0, or are we actually waiting for the first 1024 to fall? And then they're there on the map? They've already fallen? Then what's the... What was the point in the nanosecond thing then? Or maybe that's for part 2. That was not clear. It says you'll need... The wording was... You'll need to simulate the falling bytes to plan out where it will be safe to run. It doesn't... Yeah, my interpretation of that was that it's like you start at 0, they start dropping. The fact that they even mentioned it's every nanosecond. And the order, it seemed to be screaming that... Yeah, that's really unclear to me. But they don't specify your speed. Apparently you're really fast. Or apparently you're really slow, because we, Oh, no, it says, fortunately you're faster. Oh, no. But that just means we can work out where we should go. I think it's just really ambiguously worded. Like, they could have just said straight up one way or another. Either you're moving at time 0 or you're moving after they've already fallen. But the wording of the story is that they're falling as we speak. And we're moving as they're falling. That's the way I read it. Okay, fine. Well, this sentence here is the most... You'll need to simulate the falling bytes to plan out where it'll be safe to run. It doesn't say one way or the other, but the way I read it, it seems like they're falling as you're moving. Okay. In that case, that's even easier. We just have to... Obstacles will just be a set then, if neighbor in obstacles... Continue, and then the obstacles we just do. It's gonna be K. Hang on. So K for KV in bytes to items. So we're taking the first 1024. We're assuming they're already fallen. If neighbor in obstacles, then you can't walk there. None? Now I've not found a path. Let me make sure this is... So we got as far as... Got pretty close to the end. Did not... If neighbor in obstacles... Wait, so there's an obstacle at 1, 0 and 1, 1. Fine. So, okay. We got really far. Why did we not get to the goal? 6940. If neighbor equals goal. We do have equality, don't we? Yeah. Well, we got to go with the so it thinks there's too many obstacles now. I guess we should actually just draw this map out and see what's going on. One, two, three. Okay, so yeah, it was less than or equal to 1024. Oh, now that I look at the description, the very last line did actually imply you have to wait, let them fall. It says, simulate the first kilobyte falling onto your memory space. Afterward, what is the minimum number of steps needed to reach the exit? I suppose the afterward is implying after they've fallen. Okay, fine. Alright, what's going on here? So this is a set. And it looks like the set is working. There's some big obstacle stopping us from... We're getting as close as x equals 69, but we're not. Just have to draw the map. Neighbor in obstacles. Alright, first, just do this. Okay, so that is the obstacle map. The pauses where they are less than or equal to 1024. Alright, let's draw the obstacle map then. So we've got grid equals, let's say, dot for for P in obstacles grid P dot Y P dot X equals hash for row in grid print p dot y, p dot x. X has gone out of range. Wait. We've got an obstacle at 6969. Oh no, hang on. It's 0 to 17 inclusive. Isn't it? Damn it, of course it is. I'm so used to that being the wait, so the width, it goes 0 to 70 inclusive. Fuck. So this should be 71. Okay. It's got a bit of a clump at the start and a clump at the end. 286. All right, that's better. Correct. The historians aren't as used to moving around in this pixelated universe as you are. You're afraid they're not going to be fast enough to make it to the exit before the path is completely blocked. To determine how fast everyone needs to go, you need to determine the first byte that will cut off the path to the exit. In the above example, after the byte on one falls, there is still a path to the exit. However, after adding the very next byte, there is no longer a path to the exit. So in this example, the coordinates of the first byte that prevents the exit from being reachable are 6, 1. Simulate more of the bytes that are about to corrupt your memory space. What are the coordinates of the first byte that will prevent the exit from being reachable from your starting position? I mean, my first instinct is that just running BFS over and over again would the numbers don't seem that big. Well, we can try it and see. I mean, how many are we talking about? 3. Okay, that's quite a few. 3,450 iterations of BFS. So it's something like so it'd be like 3,400 something times 70 times 70. So that's like 16 million or something. I think we could do that. So we know it's reachable from 1024. Try that then. All right. Part 2. In this case, this hash. Okay, so now that we don't care about them falling like in order, we don't really need to store this as a hash map anymore. It should just be a list. Dot append that. And then when we create the obstacles, we just say set off by 1024. Just make sure we get the same answer. Okay. need this. Just hide this for now. Alright, so start with or I in range from, let's say, 1025 to length of obstacles. Alright, we'll just try the iterative approach. Just print I so I see where we're going. So we say obstacles dot add. Wait, no. Length of bytes. Obstacles dot add bytes. So just add the new bytes. So that's gonna be I. -1. No. Just do, yeah, from 1024 onwards. Obstacles.add bytes. And then we say if BFS so the same thing. Is none. Break, and then print I. Alright, see if it works. Is it gonna take a really long time? BFS. What? What happened there? Alright. It's going up fast enough. So I think we just let it run. I mean, what else? So what you can do is, a way to speed this up would be, every time you find a path, you now know that path will only be broken if an obstacle falls along that path. Right? So then every time you're adding an obstacle, you don't have to run BFS again until you see an obstacle land on that path. So that means instead of checking BFS every single time, we're checking it like a whole dimension fewer, like it's going to be much quicker. But this seemed fast enough, if it's correct. I'm suspicious now. I might have completely overlooked. Oh, but it does say what are the coordinates of the first byte that will prevent the exit from being reachable. Okay. Print. Oh, so let's do print bytes I. Still quite suspicious. So I'm gonna look at the description again. Prevent the exit from being reachable from the start. No, it seems it's pretty succinctly described. I think that is all we do. 2064. It's X and Y. Is that it? Okay. Yeah, that was easy. I mean, I like the idea of just if they had increased the numbers a bit more, then they would have kind of forced you to need to only consider bytes that break up the path you're currently, the best path you've found so far. And since they'll only happen with a far lower probability, then that massively improves your speed. But my only optimization was running the time backwards from the end. Okay, so you start with all the obstacles and remove them. Oh, okay, yeah, because that does make the searches quicker, because... Oh, does it? I don't know. It depends. At some point, you'll be fully exhausting half the map or something. Whereas, if you're finding... It depends how quickly the BFS finds the path. If we were using A star, then it would be much better, wouldn't it? Because then you would... No, if we were using A star, then I think it's better to go in the order that I went, because as long as there exists a path to the goal, A star will usually find it quite quickly, hopefully. So that the BFS runs should be quicker. But because we're using BFS, it just sort of expands a lot of the map anyway. So I guess going from time backwards is actually faster because there's just less of the map to expand most of the time. Yeah, that sort of makes sense. If I was using A star and it was using heuristics, then it will try to get to the exit a bit better. So then I would think it'd be quicker to actually find the path than to fail to find any path. So yeah, one optimization would be to use A star. Can't be bothered to write that when this BFS is so quick. Another one I would say is what I said. Once you found a path, you already know that that path will always exist until something interrupts it. So just wait until something cuts it. Okay, this whole problem was way easier than I thought. I mean, I really thought we'd be having an obstacle map which changed as you walked around, which is not much harder, but it is a creative tweak on BFS or whatever pathfinding algorithm you choose, and it is something you have to account for in your neighbor function. This problem seems small enough that A star would take longer to code than just running BFS. Yeah. Oh no, it does take longer to code. I mean, unless you've just written A star in a library and copied it in. Yeah, you need to. How long does your part 2 run? Like a minute, I think it took me, or maybe like more like 30-40 seconds. I'm printing a lot, so that's slowed it down. But I'm pretty sure I could bring that down to like a second if I wanted to, if I was bothered, by putting in the optimizations I've mentioned. I mean, this also seems like a problem that if you have written BFS before, and indeed we at this point, a lot of us probably already have because we've had so many grid problems, then if you were to just copy... In fact, I was going to do that. I was just going to literally copy my old pathfinding algorithm because it's the same. And then the problem would probably take you seconds. After the minutes I spent understanding the problem. Applied binary search to it, got 9 milliseconds. Binary search. Oh, okay, yeah, that makes sense, yeah. That is actually... Binary search is a huge improvement, yeah, because building the obstacle map takes minimal time anyway, so yeah, you just Well, I'm curious how that binary search would compare with the thing that I suggested, where you only consider if you're adding obstacles in a linear fashion, then you only rerun BFS every time you see something cross the path. I'm curious how that compares with binary search. Then they both seem to have their merits. So I believe Metalim is saying just pick a number between, like, midway between the bytes, and just take the first half of the bytes, see if you can get to the end with that. If you can, then you know that so we're trying to find the number of the byte, right, that cuts off the path somewhere between 0 and like 3000 or whatever it is. So if we start with, say, 1500, and we just take the first 1500 bytes, see if we can get from start to goal. If we can, then we know that the answer must be higher than 1500. If we can't, we know it must be below 1500. And now pick, say, 750 if we're going below, and so you're binary searching amongst the indices of the bytes to find the value, the answer. You're binary searching on the final answer, really. Searching for the byte that cuts it off, because you always know whether it's going to be in the left half or the right half. That's pretty good as well. I guess that probably would be the fastest way, yeah, because you're using a logarithmic number of steps, so it's going to be like, it should only be like 10, 11, 12 iterations of BFS, really, because that's you just have to halve the list like 10 times already, and then you're pretty much done. Python even has like some... I always write binary search myself, but there is actually stuff in Python to sort of do that. I can't remember what it's called. There's some module somewhere in Python where you can search, find the point in a list at which a certain condition stops getting met or starts getting met. I always just write binary search from scratch, though. It always helps me think about what's going on. I feel like Python already has anything if you know where to look here. Next time I might try and use that. It's good to use the built-in Pythons, because often they can be more efficient than what you're writing, but Alright, I guess people will have solved this one quickly, because if you're copying in BFS code, then it's pretty believable to get these kinds of times at this point. It's like you copy BFS in, tweak a few things, and then it should be it. But then again, I don't know, 18 seconds for part 1, still seems a bit fishy. Anyway, I told myself I wouldn't worry about the global leaderboard anymore. Private leaderboard. This one is a nice easy one for Maro, I think, because he's using Game Engine to do this. This is well suited for a game engine. Captain Coda. I don't know if Captain Coda's going to start up again. Oh, Captain still... I don't know if he is going to go in order or whether he'll just start from the latest day. Probably he'll start from the latest day when he starts doing them again, if indeed he does, or maybe he's just taking his Christmas holidays now. All right, nice easy problem. That took me under an hour. I did get kind of stuck a couple of times though, just from stupid errors. Let me have a look at Twitch. Just that code. C# RAM run. Okay. Okay, CSS. I don't think I've rated them before.
One by one, starting from the last list, and returns the answer when the path is found after removing that obstacle. Okay.
Has he already solved it? Alright, I'll rate them anyway. Alright. Thanks for... He's already finished. In that case... Yeah, I won't rate him if he's finished. Yeah, there's no one else. Alright, we'll just leave it there then. Alright. Thanks for watching, and catch you tomorrow for day 19, which might be a hard one again, because we had a really nice, easy day today. Bye-bye.